our Earth, a planet that has been a stage for countless fascinating creatures. Among the most spectacular of these were the dinosaurs, ruling the world during the Mesozoic era. These giants of history weren't just rulers by size, they were expert hunters and had a remarkable sense for navigating the world around them, making them perfectly suited to their environments. The story of the dinosaurs is one of dominance and mystery. They roamed the Earth, each species displaying unique abilities that allowed them to flourish. From the massive, peaceful giants that grazed on treetops to the stealthy and fearsome predators that stalked their prey, dinosaurs were a diverse and complex group that formed the heart of their ecosystems. However, as dominant as they were, their supremacy faced a sudden turn. What took millions of years to evolve vanished in what seems like a moment, leaving the Earth silent, with only their fossilized remains to hint at their once majestic existence. What happened on the last day of the dinosaurs? Let me take you on a journey through time, showing the evolution of Earth's most spectacular residents, from their earliest ancestors to their last days. It's a story about survival, the changes of our planet, and the life that has called it home. Join us as we explore the history of the dinosaurs, their rise to millions of years of power, and their sudden end. Dinosaurs have long fascinated the imagination of people and scientists of all ages, but there's more to these ancient beings than just their massive size and ferocious nature. Dinosaurs are a diverse group of reptiles of the clade Dinosauria. They first appeared during the Triassic period, about 230 million years ago, and became the dominant terrestrial vertebrates after the Triassic-Jurassic extinction event 201 million years ago. Their dominance continued until the end of the Cretaceous, about 66 million years ago, when the Cretaceous-Paleogene extinction event led to the extinction of most dinosaur species. The very essence of what makes a creature a dinosaur is found not just in their size or the time period they lived, but in their unique skeletal structures. Dinosaurs are characterized by their upright stance, with legs positioned directly beneath the body. This posture is a key feature distinguishing them from other reptiles, which typically have sprawling limbs. Dinosaurs are divided into two main groups based on their hip structure: the Ornithischia, or bird-hipped dinosaurs, and the Saurischia, or lizard-hipped dinosaurs. This classification is somewhat counterintuitive because birds actually evolved from theropod dinosaurs, which are part of the Saurischia group, not from the Ornithischia. Exploring the world of dinosaurs offers a window into evolutionary biology and the dynamics of life on Earth. Dinosaurs occupied every continent, and their remains have been found all around the globe, indicating their widespread presence and adaptability to different environments. This adaptability is reflected in their diverse diet and lifestyles, ranging from the ferocious carnivores like Tyrannosaurus rex to the gentle giants like Brachiosaurus that browsed on the tops of trees. The study of dinosaurs also intersects with the field of paleoclimatology, the study of ancient climates. By understanding the environmental conditions that dinosaurs lived in, scientists can gain insights into Earth's climate history and its cyclical nature. For example, evidence suggests that during much of the dinosaur era, the Earth was much warmer than it is today, with no ice caps at the poles. This warm climate supported a wide range of ecosystems, from lush forests to vast deserts, which in turn supported the diverse dinosaur fauna. Dinosaurs' extinction, often attributed to a catastrophic asteroid impact combined with volcanic eruptions and climate change, marks a significant moment in Earth's history, leading to the rise of mammals and eventually humans. This event underscores the fragility of life and the impact of global-scale environmental changes. These prehistoric giants first made their appearance on Earth around 230 million years ago, during the Triassic period. This era was a pivotal moment in the planet's history, marking the dawn of the Mesozoic era, often called the Age of Reptiles. The world back then was a very different place, with the continents assembled into a single massive supercontinent known as Pangaea. The climate was predominantly warm, creating a variety of habitats from lush forests to arid deserts, each supporting a diverse array of life. The first dinosaurs were relatively small, bipedal creatures, a far cry from the colossal giants that would later roam the Earth in the Jurassic and Cretaceous periods. These early dinosaurs were the pioneers, setting the stage for the evolutionary saga that would lead to a remarkable diversity of species. Their emergence from earlier reptilian ancestors involved subtle changes in anatomy and posture that would define the dinosaur lineage, including a more upright gait and a three-toed foot structure, which distinguished them from other prehistoric reptiles. As the Triassic period gave way to the Jurassic, approximately 201 million years ago, dinosaurs began to dominate the terrestrial ecosystems. This was facilitated by the Triassic-Jurassic extinction event, which wiped out many of the competing reptiles and opened ecological niches for dinosaurs to fill. Their dominance was not merely due to their size or strength, but also their adaptability and the evolutionary innovations that allowed them to exploit different environments and food sources. The reign of the dinosaurs spanned over 160 million years, a testament to their success as a group. During this time, they evolved into a dazzling array of shapes and sizes, from the fearsome Tyrannosaurus rex to the towering Brachiosaurus and the armored Ankylosaurus. Their legacy is not just in the fossil record, but also in our culture, where dinosaurs continue to fascinate and inspire curiosity about the natural world and our place within it. Diving into the world of dinosaurs reveals a complex and fascinating system of classification that scientists use to organize these ancient creatures into different groups. This system, deeply rooted in the study of their physical characteristics and evolutionary relationships, helps us understand the incredible diversity that existed among dinosaurs over millions of years. At the heart of dinosaur classification are two primary groups: the Ornithischia, known as bird-hipped dinosaurs, and the Saurischia, or lizard-hipped dinosaurs. This distinction is based on the structure of their pelvises, a key anatomical feature that offers insights into their evolution and lifestyle. Ornithischian dinosaurs, despite their name suggesting a connection to birds, are actually not the direct ancestors of modern birds. Instead, they are characterized by a pelvis structure that resembles that of birds, with the pubis bone pointing backward. This group includes a variety of plant-eating dinosaurs, such as the Stegosaurus with its distinctive backplates and spiked tail, and the Triceratops, known for its large bony frill and 3 facial horns. These dinosaurs were primarily herbivores, with adaptations that suited a life of grazing and browsing on the abundant vegetation of their eras. On the other side of the classification tree are the Saurischian dinosaurs, which include both the theropods and sauropodomorphs. The theropods, like the infamous Tyrannosaurus rex and the Velociraptor, were primarily carnivorous, walking on 2 legs and equipped with sharp teeth and claws for hunting. Interestingly, it is from this group that birds are believed to have evolved, a fact that underscores the complex pathways of dinosaur evolution. The sauropodomorphs, including giants such as the Brachiosaurus and Diplodocus, were long-necked herbivores that reached some of the largest sizes known to dinosaur species. Their unique body structures allowed them to access food sources out of reach for other dinosaurs, such as high tree leaves. Understanding how dinosaurs are classified not only helps us appreciate the vast array of species that once roamed the Earth, but also illuminates the evolutionary processes that led to their development. It's a testament to the adaptability and resilience of life, with each group of dinosaurs carving out its own niche in the prehistoric world. This classification system, while complex, serves as a crucial tool for paleontologists and scientists, aiding in the reconstruction of ancient ecosystems and offering insights into how life on Earth has evolved over time. The earliest dinosaurs, stepping onto the stage of Earth's vast history around 230 million years ago during the late Triassic period, marked the beginning of a new era in the planet's evolutionary saga. These pioneering species were unlike the colossal giants that would later dominate the Jurassic and Cretaceous landscapes. Instead, they were generally small, bipedal creatures, embodying the nascent features that would come to define the dinosaur lineage. Their emergence in a world recovering from the Permian-Triassic extinction event, the most severe mass extinction in Earth's history, set the stage for the evolutionary success story that dinosaurs would become. These initial dinosaurs exhibited characteristics that were crucial for their survival and eventual dominance. Their bipedal posture, with legs positioned directly underneath their bodies, was a significant adaptation. This anatomy provided them with the agility and speed necessary to navigate the diverse environments of the Triassic period, from dense forests to arid deserts. Their upright stance was a departure from the sprawling posture of many earlier reptiles, allowing for more efficient movement and energy use. Among the earliest dinosaurs were the likes of Eoraptor and Herrerasaurus, creatures that give us a glimpse into the dawn of the age of dinosaurs. Eoraptor, one of the earliest known dinosaurs, was a small, lightly built predator that lived approximately 231 million years ago in what is now Argentina. Its diet likely consisted of small animals, and its anatomy suggests it was fast and agile, characteristics beneficial for both hunting and evasion. Herrerasaurus, slightly larger and more robust, shared its habitat with Eoraptor and displayed early signs of the diverse predatory adaptations that would become more pronounced in later theropods. The environment these early dinosaurs inhabited was markedly different from today's world, with a single supercontinent, Pangaea, beginning to rift apart. This period of geological upheaval created a patchwork of ecosystems, from lush river valleys to harsh volcanic plains, fostering a hotbed of evolutionary experimentation. The varied landscapes offered numerous niches for these creatures to exploit, setting the stage for the explosive diversification of dinosaurs in the subsequent Jurassic period. The rise of dinosaurs to dominance on Earth is a story of evolution, adaptation, and survival, unfolding over millions of years since their first appearance in the late Triassic period around 230 million years ago. Initially, these early dinosaurs were not the massive giants or formidable predators that would later roam the planet. They were small, agile creatures living in a world teeming with diverse reptilian life forms, including the predecessors of modern crocodiles and the mammal-like reptiles that had survived the Permian-Triassic extinction event. The journey from these humble beginnings to becoming the dominant terrestrial vertebrates is a testament to the evolutionary prowess of dinosaurs. As the Triassic period progressed, the Earth underwent significant geological and climatic changes. The supercontinent Pangaea began to rift apart, leading to the formation of new landmasses and ocean basins. This tectonic activity created a variety of new habitats and ecological niches, setting the stage for evolutionary experimentation. Dinosaurs, with their bipedal stance and versatile adaptations, were well suited to take advantage of these new opportunities. Their upright posture allowed for more efficient locomotion and stamina, enabling them to cover greater distances in search of food and resources. Additionally, the variety in their diets, from herbivorous to carnivorous lifestyles, allowed them to exploit different ecological niches. One of the key factors in the rise of dinosaurs to dominance was the Triassic-Jurassic extinction event, occurring approximately 201 million years ago. This event wiped out many of the competing reptilian groups, leaving ecological niches vacant and reducing competition for resources. Dinosaurs, having survived this extinction event, began to diversify rapidly, filling the gaps left by the disappeared species. This diversification was not just in size and diet, but also in their behaviors and reproductive strategies. Some developed complex social behaviors, while others evolved novel ways of defending themselves, such as armor and horns. By the Jurassic period, dinosaurs had become the most prominent group of terrestrial animals. The era saw the emergence of the iconic long-necked sauropods, such as the Brachiosaurus and Diplodocus, which were among the largest land animals ever to exist. Their size was a defense mechanism against predators and allowed them to reach high vegetation. The Jurassic also saw the rise of powerful predators like Allosaurus, which capitalized on their size, speed, and strength to become top predators. The Cretaceous period brought further diversification and the development of some of the most well-known dinosaurs, including the fearsome Tyrannosaurus rex and the horned Triceratops. This period also saw the evolution of the first true birds from theropod ancestors, highlighting the adaptive flexibility of dinosaurian life. Dinosaur evolution was heavily influenced by a series of environmental changes that swept across the Earth over the millions of years they dominated the landscape. These changes were not uniform, but varied greatly over time and space, impacting different dinosaur species in myriad ways. Understanding these environmental shifts is crucial to comprehending how dinosaurs adapted and evolved to become the diverse and often dominant life forms of their epochs. One of the most significant environmental factors was the breakup of the supercontinent Pangaea, which began in the late Triassic period and continued throughout the Mesozoic era. This tectonic shift gradually divided the once unified landmass into smaller continents and large islands, leading to the isolation of dinosaur populations and the creation of distinct ecological zones. The fragmentation of habitats drove evolutionary divergence as isolated dinosaur populations adapted to their specific environments, leading to the emergence of new species through the process of allopatric speciation. Climate played a pivotal role in shaping dinosaur evolution. The Mesozoic era, often referred to as the Age of Dinosaurs, saw a range of climatic conditions, from the warm and dry climates of the Triassic to the more humid and warmer climates of the Jurassic and Cretaceous periods. These changing climates influenced vegetation patterns, availability of water resources, and the types of prey and predators present, all of which had direct impacts on dinosaur survival and adaptation strategies. For example, the evolution of large herbivorous dinosaurs like the sauropods was facilitated by the abundance of vegetation in the Jurassic, while the diversification of carnivorous dinosaurs was likely driven by the available prey species. Volcanic activity and associated atmospheric changes were another critical factor. Large volcanic eruptions could have drastically altered the atmosphere, affecting climate and food availability. The release of ash and gases into the atmosphere could lead to cooling periods, volcanic winters, or, over longer periods, contribute to warming by increasing atmospheric levels of carbon dioxide. These shifts could trigger mass extinctions or force dinosaurs to adapt to new conditions, leading to evolutionary changes. Sea level fluctuations also played a crucial role in dinosaur evolution. Throughout the Mesozoic era, periods of significant sea level rise created shallow inland seas and expanded coastal habitats. These changes would have altered available habitats for dinosaurs, potentially encouraging the development of new species adapted to these environments. Conversely, periods of low sea levels would have exposed new lands for colonization, offering dinosaurs new ecological niches to explore and exploit. The connection between these environmental factors and dinosaur life was complex and dynamic. Adaptations such as changes in size, diet, social behavior, and reproductive strategies can be seen as responses to the challenges and opportunities presented by their changing world. For instance, the development of complex social behaviors in some dinosaur species may have been a strategy to navigate the challenges of finding food and protecting against predators in fluctuating environments. The Triassic period, which spanned from about 252 to 201 million years ago, marked the dawn of a new era following the most catastrophic mass extinction event in Earth's history, the Permian-Triassic extinction. This period set the stage for the Age of Dinosaurs and was characterized by a world in a state of recovery and dramatic transformation. The Triassic period is the first of three periods that make up the Mesozoic era, followed by the Jurassic and the Cretaceous periods. During the Triassic, the Earth was vastly different from today, with unique climates, landscapes, and life forms that laid the groundwork for the evolution of dinosaurs and many other species. At the beginning of the Triassic, the Earth's continents were still assembled into the supercontinent Pangaea, which encompassed nearly all the land masses. This configuration had a profound impact on the global climate and the distribution of ecosystems. The interior of Pangaea was arid and desert-like, with extreme temperature fluctuations between day and night due to the vast distance from the moderating influence of the oceans. Near the coasts and in regions broken up by the Tethys Sea, The climate was more humid, supporting diverse plant life and the ecosystems dependent on it. The recovery from the Permian-Triassic extinction was slow, and the early Triassic was a time of ecological simplicity. However, as the period progressed, life began to flourish once again. In the oceans, marine reptiles such as ichthyosaurs and nothosaurs became dominant predators, while on land, the first dinosaurs began to appear by the mid to late Triassic. The plant life of the period was dominated by ferns, cycads, and the ancestors of modern conifers, which provided the necessary food resources for herbivorous reptiles. The Triassic also witnessed significant volcanic activity, which contributed to the period's climate variations and may have played a role in environmental and evolutionary changes. These volcanic events released large amounts of carbon dioxide, leading to warmer global temperatures and influencing the distribution of ecosystems across Pangaea. As the Triassic period progressed, the supercontinent Pangaea began to rift apart, leading to the formation of the Atlantic Ocean and the initial stages of continental drift that would eventually shape the modern world's geography. This rifting also created new coastlines and habitats, further encouraging biodiversity and the evolution of new species. The end of the Triassic period was marked by another mass extinction event, which, while not as devastating as the one that ended the Permian, led to significant changes in the Earth's biosphere. This extinction cleared the way for the dominance of dinosaurs in the Jurassic period and set the stage for the next chapter in the Earth's evolutionary history. Among the earliest dinosaurs that roamed the Earth during the Triassic period were small bipedal creatures, significantly different from the colossal giants and fearsome predators that would evolve later. These initial dinosaurs were relatively small and agile, adapted to the varied environments of a world still dominated by vast deserts and scattered patches of lush vegetation near water sources. One of the earliest known dinosaurs is Eoraptor, a lithe carnivorous dinosaur that lived approximately 231 million years ago in what is now Argentina. Eoraptor's discovery has provided invaluable insights into the early evolutionary stages of dinosaurs, highlighting characteristics that would define the group. With a lightweight body, sharp teeth, and a versatile diet, Eoraptor represents a key ancestor of later dinosaur lineages. Another significant Triassic dinosaur is Herrerasaurus, also from Argentina, which lived around the same time as Eoraptor. Herrerasaurus was larger and more robust, with powerful jaws and teeth that suggest a primarily carnivorous diet. Its anatomy, particularly its hip structure and limb proportions, offers clues about the early diversification of dinosaurs and their adaptation strategies for survival and hunting. Plateosaurus, a herbivorous dinosaur from the late Triassic period, represents another branch of the dinosaur family tree. Found in what is now Germany and other parts of Europe, Plateosaurus was a sauropodomorph, a group that would give rise to the giant sauropods of the later Mesozoic era. Unlike its massive descendants, Plateosaurus was medium-sized, but already exhibited characteristics such as a long neck and tail, which would become more pronounced in sauropods. The Triassic period also saw the emergence of Coelophysis, a slender, carnivorous dinosaur that lived around 210 million years ago in what is now the southwestern United States. Coelophysis is one of the best understood early dinosaurs, thanks to numerous well-preserved fossils. It showcases the evolutionary trend towards efficient bipedal locomotion and predation, traits that would be refined in the theropod lineage leading to birds. These early dinosaurs were pioneers in a world undergoing dramatic changes, from the breakup of the supercontinent Pangaea to shifting climates and evolving ecosystems. Their appearance during the Triassic period represents the initial steps in the evolution of dinosaurs, laying the foundation for their dominance in the subsequent Jurassic and Cretaceous periods. As the curtain rose on the Mesozoic era with the Triassic period, the stage was set for a remarkable evolutionary play, with the earliest dinosaurs adapting to a world that was vastly different from the one we know today. In the aftermath of the Permian-Triassic extinction event, the most severe mass extinction in Earth's history, the surviving life forms faced a planet in recovery, with new niches to fill and challenges to overcome. The dinosaurs that emerged during this time, around 252 to 201 million years ago, displayed a remarkable array of adaptations that enabled them to thrive in the diverse environments of the Triassic world. The Triassic landscape was dominated by the supercontinent Pangaea, which presented a range of ecosystems from arid deserts to lush river valleys. This geographical diversity required the early dinosaurs to develop a variety of survival strategies. For instance, their bipedal posture, which was a significant departure from the sprawling stance of many earlier reptiles, allowed for more efficient movement across the varied terrains. This adaptation was crucial for both predatory dinosaurs, which needed speed and agility to catch prey, and herbivorous species that required mobility to browse for food and evade predators. The varied diet of Triassic dinosaurs was another key adaptation. Carnivorous dinosaurs, such as Herrerasaurus and Coelophysis, had sharp teeth and claws for hunting, indicating a diet that primarily consisted of other vertebrates. These predators were adapted to a life of chasing and capturing prey, with features like forward-facing eyes for depth perception and powerful hind limbs for sprinting. On the other hand, early herbivorous dinosaurs, such as Plateosaurus, developed specialized teeth and digestive systems to process the tough plant material that made up their diet. This diversification in feeding strategies allowed dinosaurs to exploit different ecological niches, reducing competition and enabling coexistence among various species. Thermoregulation, or the ability to maintain a stable internal body temperature, was another critical adaptation for dinosaurs living in the fluctuating climates of the Triassic. While the exact mechanisms of dinosaur thermoregulation remain a topic of scientific debate, features such as the positioning of their limbs beneath their bodies may have helped to minimize heat loss and maintain an active lifestyle, even in cooler temperatures. The social behavior of some Triassic dinosaurs may have also played a role in their adaptation to the environment. Evidence suggests that certain species, like Coelophysis, may have lived and hunted in groups. This social structure could have provided advantages in locating food, protecting against predators, and caring for young. Such behaviors indicate a level of social complexity that would have supported their survival and reproductive success in the diverse and sometimes harsh environments of the Triassic. During the Jurassic period, which lasted from about 201 to 145 million years ago, the Earth underwent significant transformations that reshaped its continents and climates, paving the way for new ecosystems and the flourishing of dinosaur life. This era, nestled between the Triassic and Cretaceous periods, is often depicted as a time of lush landscapes and gigantic dinosaurs, a portrayal that is supported by the profound geological and climatic changes of the period. As the Jurassic era dawned, the supercontinent Pangaea continued to rift apart, a process that had begun in the late Triassic. This breakup led to the gradual formation of the Atlantic Ocean as the land masses of Laurasia and Gondwana started to take shape. Laurasia, in the northern hemisphere, would eventually become North America and Eurasia, while Gondwana, in the southern hemisphere, would split into what are now Africa, South America, Antarctica, India, and Australia. This division of the supercontinent had far-reaching effects on global climate, ocean circulation, and the distribution of plants and animals, including dinosaurs. The climate of the Jurassic was predominantly warm and humid, with higher levels of atmospheric carbon dioxide than present-day Earth. This greenhouse effect, combined with the distribution of continents and seas, created a relatively uniform global climate, with less temperature variation from the equator to the poles than is experienced today. These conditions supported extensive tropical and subtropical forests, which covered much of the planet, providing diverse habitats for dinosaurs and other life forms. The warm, moist environment of the Jurassic was ideal for the growth of plants, including the rise of gymnosperms, non-flowering seed plants such as conifers, cycads, and ginkgos. These plants dominated the landscape, forming vast forests that served as a crucial food source and habitat for many dinosaur species. The abundance of vegetation supported a wide range of herbivorous dinosaurs, which in turn provided prey for carnivorous dinosaurs. Marine environments also experienced significant changes during the Jurassic. As Pangaea split and new seas formed, marine reptiles such as ichthyosaurs, plesiosaurs, and pliosaurs thrived in the expanded oceanic habitats. Coral reefs began to develop in shallow, warm waters, adding to the biodiversity of marine ecosystems. The shifting continents and evolving climates of the Jurassic period created a world that was vastly different from the Triassic that preceded it. These changes facilitated the diversification and spread of dinosaurs, allowing them to become the dominant terrestrial vertebrates of the time. The Jurassic also saw the evolution of important plant and animal groups that would shape ecosystems for millions of years to come. One of the most iconic dinosaurs of the Jurassic period is the Brachiosaurus, known for its towering neck and massive size. This gentle giant was a sauropod, a group of herbivorous dinosaurs characterized by their long necks and tails, small heads, and 4 thick pillar-like legs. Brachiosaurus, with its unique body proportions that included longer front legs than hind legs, could reach heights of up to 13 meters. About 43 feet, allowing it to browse for leaves high up in trees. Its presence across what is now North America and possibly Africa underscores the widespread distribution of sauropods during the Jurassic. Another standout from the Jurassic is the Stegosaurus, famous for its distinctive row of bony plates along its back and spiked tail, which likely served as a defense mechanism against predators. This plant-eating dinosaur roamed the landscapes of what is now North America with its peculiar posture, characterized by a heavily built body, short forelimbs, and a small head, making it one of the most recognizable dinosaurs of all time. The Allosaurus, a fearsome predator of the Jurassic, was the apex predator of its time in many ecosystems. This carnivorous dinosaur was equipped with sharp teeth and claws, making it a formidable hunter. Its fossils have been primarily found in North America and Portugal, providing evidence of its wide range. Allosaurus's size, which could reach up to 12 meters, about 39 feet in length, combined with its agility, made it a dominant predator capable of taking down large prey, including juvenile sauropods. The Diplodocus is another iconic sauropod of the Jurassic period, known for its extraordinary length, which could exceed 30 meters, about 98 feet. Its long neck and tail, which accounted for much of its length, and its peg-like teeth, suited for stripping leaves off branches, made it an efficient feeder. The Diplodocus's fossils, found primarily in the Morrison Formation of North America, offer valuable insights into the life of sauropods and their role in Jurassic ecosystems. During the Jurassic period, dinosaurs achieved sizes that far surpass any land-dwelling animals found on Earth today. The growth to such immense sizes was not a simple process, but the result of a complex interplay of environmental conditions, evolutionary pressures, and biological mechanisms that allowed these prehistoric giants to dominate the landscapes of their time. One key factor contributing to the large size of Jurassic dinosaurs, particularly sauropods like Brachiosaurus and Diplodocus, was the abundance of food resources. The warm, humid climate of the Jurassic period supported lush vegetation, including vast forests of conifers, cycads, and ferns. This rich plant life provided an ample food supply for herbivorous dinosaurs, enabling them to consume the massive amounts of plant material needed to fuel their growth. Another important factor was the dinosaurs' efficient respiratory system. Unlike modern reptiles, dinosaurs had a bird-like respiratory system, which is more efficient at oxygen exchange. This system, which includes air sacs, helped to supply the large amounts of oxygen needed for their muscular activity and metabolic processes. The high levels of oxygen in the Jurassic atmosphere further facilitated this process, supporting the dinosaurs' growth and activity levels. The structure of dinosaur bones also played a role in their large size. Many dinosaurs had a unique bone structure with large, air-filled cavities, making their skeletons strong, yet relatively lightweight. This adaptation allowed them to support massive bodies without the need for excessively heavy bones, enabling them to grow to large sizes while remaining agile and mobile. Evolutionary pressures and natural selection also contributed to the trend toward larger sizes. In many cases, being large offered advantages in terms of defense against predators, access to higher vegetation for herbivores, and dominance within social hierarchies. Over time, natural selection favored larger individuals, leading to an evolutionary trend known as Cope's rule, which observes that animal lineages tend to increase in size over evolutionary time. The reproductive strategies of dinosaurs may have contributed to their size. Larger dinosaurs could lay more eggs, increasing their chances of reproductive success. The survival strategy of producing many offspring, some of which would grow to adulthood, could have supported the evolution of larger body sizes as a way to maximize reproductive output. The long growth periods of dinosaurs allowed them to reach sizes that would be impossible for animals with shorter lifespans. Some dinosaurs likely lived for decades, with slow, continuous growth throughout their lives. This extended growth period, combined with the availability of resources and efficient physiology, enabled them to achieve their gigantic proportions. The Cretaceous period, which spanned from about 145 to 66 million years ago, marked the last chapter of the Mesozoic era, often heralded as the Age of Dinosaurs. This era witnessed significant evolutionary advancements and the appearance of new dinosaur species, contributing to an unprecedented level of diversity among these prehistoric creatures. The Cretaceous period brought forth a variety of new dinosaur species, each adapted to the changing environments and ecological niches of their time. One of the most iconic dinosaurs to emerge during the Cretaceous was the Tyrannosaurus rex, often simply referred to as T-Rex. This massive predator, with its powerful jaws and sharp teeth, roamed the landscapes of what is now North America. The T-Rex, which lived towards the end of the Cretaceous period, around 68 to 66 million years ago, has become synonymous with the term dinosaur for many people, symbolizing the might and ferocity of these prehistoric creatures. Another notable group that thrived during the Cretaceous was the ceratopsians, or horned dinosaurs, with Triceratops being one of the most well-known members. Triceratops, characterized by its large, bony frill and 3 horns on its face, inhabited the areas of North America around 68 to 66 million years ago. These herbivores were among the last dinosaurs standing before the mass extinction event that closed the Mesozoic era. The Cretaceous also saw the rise of the hadrosaurs, or duck-billed dinosaurs, such as Edmontosaurus, which were known for their broad, flat beaks adapted for shredding plant material. Hadrosaurs were widespread, with fossils found across parts of what are now North America, Asia, and Europe. Their success can be attributed to their efficient feeding mechanisms and possibly complex social behaviors. Another significant addition to the dinosaur family tree during the Cretaceous was the Spinosaurs, including Spinosaurus, which is believed to have been one of the largest carnivorous dinosaurs ever to exist. Spinosaurus, distinguished by its long, narrow skull and sail-like structure on its back, is thought to have lived both on land and in water, similar to modern crocodiles, hunting both terrestrial and aquatic prey. The armored dinosaurs, or ankylosaurs, such as Ankylosaurus, also made their mark during the Cretaceous. Ankylosaurus, with its heavily armored body and club-like tail, was well equipped to defend itself against predators. It roamed the landscapes of North America around 68 to 66 million years ago. The Cretaceous period was not only a time of diversification for dinosaurs, but also saw significant changes in plant life, with the rise of flowering plants, angiosperms, altering ecosystems and providing new food sources. This shift in vegetation may have influenced the evolution and spread of various herbivorous dinosaurs, further shaping the dynamics of Cretaceous ecosystems. During this Cretaceous period, a significant evolutionary shift in plant life occurred that had a profound impact on the ecosystems of the time, particularly affecting herbivorous dinosaurs. This period saw the first widespread appearance and diversification of flowering plants, or angiosperms, a development that would drastically alter the landscape and provide new sources of nutrition for a variety of organisms. Before the rise of flowering plants, the dominant vegetation consisted of gymnosperms, including conifers, cycads, and ferns. These plants had been the primary food source for herbivorous dinosaurs, offering a diet that supported their growth and survival. However, the emergence of angiosperms introduced a new dynamic into these prehistoric ecosystems. Flowering plants evolved rapidly, spreading to various habitats and eventually dominating many landscapes by the late Cretaceous. This explosion of angiosperm diversity is often referred to as the Cretaceous terrestrial revolution. The rise of flowering plants had several implications for herbivorous dinosaurs. Firstly, it provided them with a new and varied source of food. Angiosperms tend to grow more quickly than gymnosperms and can occupy a wide range of ecological niches, from dense forests to open grasslands. This meant that herbivorous dinosaurs had access to a more abundant and diverse food supply, potentially supporting larger populations and facilitating the evolution of new species. The nutritional content of flowering plants, including their leaves, fruits, and seeds, may have offered advantages over the more ancient gymnosperms. The availability of fruits and seeds in particular could have provided a rich source of energy and nutrients, contributing to the dietary needs of these dinosaurs and possibly influencing their feeding behaviors and physical development. The interaction between herbivorous dinosaurs and flowering plants likely went both ways, with dinosaurs playing a role in the spread and diversification of these plants. Dinosaurs could have acted as pollinators, inadvertently transferring pollen as they moved from plant to plant. Additionally, the consumption and subsequent dispersal of seeds by dinosaurs could have aided in the propagation of flowering plants across various environments. The evolutionary arms race between plants and herbivores also saw advancements in plant defense mechanisms, such as the development of thorns and toxic chemicals, which would have influenced the feeding patterns and adaptations of herbivorous dinosaurs. In response, these dinosaurs may have evolved more specialized feeding strategies or digestive systems capable of handling a variety of plant materials, including those with defensive properties. Through the study of fossil remains, footprints, nesting sites, and other paleontological discoveries, scientists have been able to piece together a vivid picture of dinosaur life during this era, revealing insights into how these magnificent creatures interacted with their environment and each other. One of the most compelling pieces of evidence comes from fossilized dinosaur nests and eggs, which have been found in various locations around the world. These findings offer clues about the reproductive behaviors of dinosaurs, suggesting that some species exhibited parental care. For instance, the discovery of nests with fossilized eggs, some containing embryonic remains, indicates that certain dinosaurs, like the Hadrosaur maiasaura, returned to the same nesting sites repeatedly and may have cared for their young after they hatched. This behavior is reminiscent of modern birds, which are considered the closest living relatives of dinosaurs. Trackways, or fossilized footprints, provide another window into the daily lives of Cretaceous dinosaurs. These preserved tracks have been found in patterns that suggest social behavior, such as herding among various dinosaur species. For example, parallel trackways of ornithopods indicate that these herbivores moved together in groups, possibly as a strategy for protection against predators. Similarly, the spacing and orientation of theropod tracks have led some scientists to hypothesize that certain carnivorous dinosaurs may have hunted in packs, coordinating their movements to stalk and ambush prey. The arrangement and location of fossil bones can also offer insights into dinosaur behavior. Sites where large numbers of a single dinosaur species have been found together suggest that some dinosaurs lived in herds or congregations. This herd behavior, seen in species like the horned dinosaur Triceratops, could have provided advantages in terms of defense and foraging. On the other hand, the discovery of predator and prey fossils in close proximity can indicate hunting or scavenging behavior, as seen in the dramatic fossilized scenes where predators like Velociraptor are found in combat with herbivores like Protoceratops. Additionally, the physical adaptations of dinosaurs provide clues to their behaviors. The development of specialized teeth, claws, and other anatomical features point to a variety of feeding strategies, from the slicing teeth of carnivores adapted to cutting flesh to the flat, grinding teeth of herbivores suited for processing plant material. The evolution of elaborate horns, frills, and crests in dinosaurs such as Triceratops, and the duck-billed hadrosaurs suggest that these features may have been used in social displays, for defense, or in competition for mates. The study of coprolites, or fossilized dinosaur feces, has contributed to our understanding of dinosaur diets and feeding behaviors. Analysis of coprolites has revealed the remains of digested plant material, bones, and even parasites, offering a direct look at what some Cretaceous dinosaurs ate and the challenges they faced from disease and parasitism. Dinosaurs exhibited a wide range of hunting and feeding behaviors that were as diverse as the dinosaurs themselves. These behaviors were closely linked to their physical adaptations, the environments they inhabited, and the available prey or plant resources. By examining the anatomical features of different dinosaur species and the ecological contexts in which they lived, scientists have been able to infer a variety of strategies dinosaurs used for hunting and feeding. Carnivorous dinosaurs, or theropods, such as the iconic Tyrannosaurus rex and the smaller but agile Velociraptor, were primarily hunters. The sharp, serrated teeth of T-Rex were perfect for tearing through the flesh of its prey, while its powerful jaws could exert one of the strongest bite forces of any terrestrial animal. The T-Rex's massive size and strength, combined with its keen sense of smell, made it a formidable predator capable of taking down large herbivores. Velociraptor, on the other hand, was smaller and relied on its speed, agility, and intelligence, as well as a deadly sickle-shaped claw on each foot, to ambush and overpower smaller prey or perhaps scavenge meals from larger predators' kills. Evidence suggests that some carnivorous dinosaurs may have hunted in packs, similar to the behavior of modern wolves. Pack hunting could have allowed these predators to take down prey much larger than themselves through coordinated attacks, increasing their hunting success rate. Fossil sites showing multiple individuals of species like Allosaurus found together with large herbivorous dinosaurs support the theory of social hunting among certain theropods. Herbivorous dinosaurs employed a variety of feeding strategies, largely determined by their physical adaptations. Sauropods, such as Brachiosaurus and Diplodocus, reached enormous sizes and had long necks that allowed them to feed on the foliage of tall trees, accessing food sources that were out of reach for other herbivores. Their peg-like teeth were suited for stripping leaves off branches, which were then swallowed whole and processed in their vast digestive systems. Ornithischian dinosaurs, like the duck-billed hadrosaurs and the horned ceratopsians, including Triceratops, developed more specialized teeth and jaws for processing plant material. Hadrosaurs had hundreds of tightly packed teeth that formed a continuous grinding surface, ideal for chewing tough, fibrous plants. Ceratopsians, with their beaked mouths and rows of slicing teeth, could cut and crush a variety of vegetation. Some dinosaurs may have also engaged in opportunistic feeding behaviors, such as scavenging. In environments where food resources were scarce, carnivorous dinosaurs might have fed on carcasses left by other predators or those that died from other causes, ensuring their survival in challenging conditions. Evidence of social behavior among dinosaurs, which ranges from fossilized footprints to nesting sites, provides a fascinating glimpse into the complex lives these creatures led millions of years ago. This evidence supports the idea that certain dinosaurs not only interacted with each other, but also formed groups that might have hunted, migrated, and even cared for their young together. One compelling piece of evidence for social behavior in dinosaurs comes from the discovery of fossilized footprints. These trackways show patterns of movement that suggest some species of dinosaurs moved together in groups. For example, parallel tracks of large herbivorous dinosaurs, such as sauropods, indicate that these giants might have migrated in herds, possibly to find food or suitable nesting grounds. Similarly, groupings of theropod tracks suggest that some carnivorous dinosaurs might have hunted in packs, coordinating their movements to outmaneuver prey. Another significant indicator of social behavior is the discovery of nesting sites, where multiple individuals of the same species have nested close together. In Montana, for example, scientists have uncovered areas dense with the nests of Maiasaura, a duck-billed dinosaur. These nesting sites contained eggs, hatchlings, and juveniles, suggesting that Maiasaura parents may have returned to the same locations to nest and that they provided care for their young. The presence of nests in close proximity to each other indicates a level of social organization and perhaps communal nesting practices. Additionally, the fossil record has revealed instances of dinosaurs dying in groups, which some paleontologists interpret as evidence of social living. Mass grave sites, where individuals of the same species are found together, could indicate that these dinosaurs lived in herds or packs and might have faced a common disaster or challenge that led to their simultaneous demise. Such findings suggest not only social interaction, but also the possibility of complex herd dynamics and social structures. The physical features of some dinosaurs also hint at social behavior. For instance, the elaborate horns and frills of ceratopsians like Triceratops and the distinctive crests of hadrosaurs such as Parasaurolophus might have served purposes beyond defense or feeding, such as signaling to other members of their species. These features could have played a role in mating displays, territorial disputes, or other forms of social communication, indicating a level of social complexity. Studies of bone beds, where the remains of multiple dinosaurs are found together, have provided insights into the social lives of predatory dinosaurs. Some bone beds suggest that large theropods like Allosaurus may have hunted or scavenged in groups. While definitive proof of pack hunting is challenging to establish, the spatial arrangement of fossils and the presence of multiple individuals of varying ages in a single location suggest social interactions. The reproduction and parental care of dinosaurs have been subjects of intense study and speculation among paleontologists. Through the examination of fossils, including nests, eggs, and juvenile dinosaur remains, scientists have gathered evidence that sheds light on these aspects of dinosaur biology, revealing a complex and varied picture across different species. Dinosaurs reproduced by laying eggs, as confirmed by the discovery of numerous dinosaur nests and eggs across the world. These eggs vary in size, shape, and structure, indicating a wide range of reproductive strategies among different dinosaur species. For example, the eggs of sauropods were relatively small compared to their massive adult size, suggesting that these dinosaurs laid many eggs to increase the chances of offspring survival. In contrast, theropods, like the fearsome Tyrannosaurus rex, laid larger eggs, which might have contained more developed embryos, requiring more parental investment before and after hatching. The discovery of dinosaur nesting sites has provided valuable insights into their reproductive behavior. Some sites contain nests that are closely spaced and arranged in patterns, suggesting that certain dinosaurs, such as the hadrosaur Maiasaura, nested in colonies. This behavior could have offered advantages, including protection from predators and the opportunity for communal care of the young. Fossilized remains of Maiasaura have shown evidence of rapid growth rates, which some scientists interpret as a sign of parental care, providing food and protection to help their offspring grow quickly and reduce their vulnerability to predators. Evidence of parental care extends beyond hadrosaurs. In some theropod species, such as Oviraptor, adults have been found in close association with nests, sometimes in positions that suggest they were brooding the eggs, much like birds do today. This behavior indicates that at least some theropods provided care for their eggs, and possibly their hatchlings, by guarding the nest and regulating the temperature necessary for development. The structure and composition of dinosaur eggs themselves also provide clues to reproductive strategies and parental care. Some dinosaur eggs have been found with complex layers and textures, suggesting mechanisms for gas exchange and protection. Additionally, the arrangement of eggs in nests, often in circular patterns, and the presence of clutches with multiple eggs indicate that dinosaurs invested significant effort into the placement and care of their offspring. While direct evidence of juvenile care beyond the egg stage is more challenging to ascertain, the growth patterns inferred from fossilized bones suggest that some dinosaurs grew at rates that might have required parental support. The social behavior observed in trackways and inferred from the fossil record of grouped individuals could also imply that young dinosaurs benefited from living in family groups or herds, where they could learn from adults and gain protection. Dinosaurs developed a myriad of unique adaptations that allowed them to thrive in diverse environments and become one of the most successful groups of animals in Earth's history. These adaptations ranged from physical characteristics to behavioral traits, enabling dinosaurs to exploit various ecological niches and dietary preferences. One of the most significant adaptations among dinosaurs was their wide variety of feeding mechanisms. Herbivorous dinosaurs, for instance, developed specialized teeth and jaws for processing plant material. The hadrosaurs, or duck-billed dinosaurs, had hundreds of tightly packed teeth that formed a continuous grinding surface, ideal for chewing tough, fibrous plants. In contrast, sauropods, the giant, long-necked dinosaurs, had peg-like teeth suited for stripping leaves off branches, which they could then swallow whole, relying on their massive digestive systems to break down the food. Carnivorous dinosaurs, such as the theropods, showcased adaptations for hunting and consuming meat. The Tyrannosaurus rex, for example, had powerful jaws with large serrated teeth, capable of delivering a devastating bite to its prey. Smaller predators like Velociraptor possessed sharp, curved claws on their feet, which they likely used to grasp and subdue their victims. Another remarkable adaptation was the development of defensive mechanisms. The stegosaurs had large, bony plates along their backs and spikes on their tails, which could have been used for protection against predators. Ankylosaurs took defense to another level with their armored bodies and club-like tails, making them one of the most heavily fortified dinosaurs. Dinosaurs also adapted to their environments through locomotion. The bipedal stance of many theropods allowed for efficient movement and agility, crucial for hunting or scavenging. On the other hand, quadrupedal dinosaurs like the sauropods and ceratopsians had robust legs capable of supporting their massive bodies and facilitating migration over long distances in search of food or mates. Some of the most intriguing adaptations among dinosaurs were related to social behavior and communication. The crests and frills seen in species like Parasaurolophus and Triceratops may have served multiple functions, including species recognition, sexual selection, and sound production for communication within their groups. Dinosaurs' reproductive strategies also displayed adaptability. The evolution of hard-shelled eggs allowed dinosaurs to lay their eggs in a variety of environments, protecting the developing embryos from desiccation and predators. Nesting behaviors, as seen in the carefully arranged nests of some species, suggest that certain dinosaurs invested considerable effort into the care and protection of their offspring. The skin of dinosaurs, as inferred from fossil impressions and related evidence, ranged from scaly textures reminiscent of modern reptiles to more complex structures associated with feathers. In many herbivorous dinosaurs, like the massive sauropods and the armored ankylosaurs, skin textures often included tough, scaly coverings. These scales likely served as a first line of defense against predators and environmental hazards, protecting the dinosaurs from injuries and infections. Additionally, the bony plates and spikes that characterize species such as Stegosaurus and Ankylosaurus were extensions of their skin, providing extra protection against predators. For theropod dinosaurs, particularly those within the group known as Coelurosauria, which includes the ancestors of modern birds, feathers were a significant adaptation. Initially, scientists believed feathers were primarily for flight in birds, but discoveries of feathered dinosaurs that could not fly have expanded our understanding of feather functions. Feathers likely served multiple purposes, including insulation, helping these dinosaurs regulate their body temperature. This thermoregulatory function would have been especially beneficial for maintaining activity levels in varying climates, supporting the hypothesis that some dinosaurs were endothermic or warm-blooded to some degree. Beyond insulation, feathers in dinosaurs also played roles in display and communication. The discovery of dinosaurs like Velociraptor and the larger Yutyrannus, which had feathers despite their inability to fly, suggests that feathers could have been used for visual displays in mating rituals, to assert dominance, or to scare off rivals and predators. The coloration and pattern of feathers, which can sometimes be inferred from fossil evidence, might have allowed for species recognition and social signaling within groups of dinosaurs. In smaller bird-like dinosaurs, such as Archaeopteryx, feathers provided the additional function of aiding in flight or gliding. marking the evolutionary transition towards modern birds. This capability would have opened new ecological niches to these creatures, allowing them to escape predators, reach new feeding grounds, and explore different habitats. Differences in size and shape among dinosaurs were crucial factors that affected their survival, enabling these creatures to adapt to a wide range of habitats and to fill various ecological niches throughout the Mesozoic era. The incredible diversity in the physical forms of dinosaurs, from the towering sauropods to the nimble theropods, illustrates the evolutionary innovations that allowed them to become one of the most successful groups of animals in Earth's history. Size played a significant role in the survival strategies of dinosaurs. Larger dinosaurs, such as the sauropods Brachiosaurus and Diplodocus, benefited from their massive size in several ways. Their great height allowed them to access food sources that were out of reach for other herbivores, feeding on the high foliage of trees. Moreover, their sheer size provided a defense mechanism against predators. Few carnivores could take down an adult sauropod due to its size and strength. However, being large also required vast amounts of food and led to slower reproduction rates, as larger dinosaurs had longer growth periods before reaching maturity. In contrast, smaller dinosaurs, like the theropod Velociraptor, used their size to their advantage in different ways. Their smaller stature allowed for agility and speed, making them effective hunters capable of quick attacks and rapid changes in direction. Being smaller also meant that these dinosaurs required less food to survive and could reproduce more quickly, traits that could be advantageous in environments where resources were limited or fluctuating. The shape of dinosaurs also significantly influenced their survival. Dinosaurs evolved a variety of body shapes tailored to their specific lifestyles and environments. For instance, the aerodynamic bodies and feathered limbs of dromaeosaurids, such as Velociraptor, were likely adaptations for pursuing prey, allowing for bursts of speed and agility. The unique body shape of ankylosaurs, with their low-slung, heavily armored bodies and club-like tails, was a specialization for defense, deterring predators with their formidable protective features. The shape of a dinosaur's skull and teeth provide insights into its diet and feeding strategies, which directly impacted survival. Carnivorous dinosaurs had sharp, serrated teeth designed for slicing flesh, while herbivorous dinosaurs exhibited a range of teeth adaptations for processing plant material, from the grinding molars of hadrosaurs to the shearing teeth of ceratopsians. These adaptations ensured that dinosaurs could exploit a variety of food sources, reducing competition and allowing for coexistence among diverse species. The evolution of distinct size and shape adaptations among dinosaurs was a response to the challenges posed by their environments, including competition for resources, predation pressure, and changing climates. These physical characteristics not only allowed dinosaurs to occupy a wide array of ecological niches, but also provided the flexibility needed to adapt to the Earth's dynamic ecosystems over millions of years. The spread of dinosaurs across the continents is a fascinating tale of geological change and evolutionary adaptation. During the Mesozoic era, which spanned from about 252 to 66 million years ago, the configuration of the Earth's continents underwent significant transformations. These shifts in the planet's land masses played a crucial role in the distribution and diversification of dinosaur species. At the dawn of the Mesozoic, the Earth's continents were assembled into a single supercontinent known as Pangaea. This massive landmass provided a relatively uniform environment where the early dinosaurs, emerging around 230 million years ago during the late Triassic period, could roam freely without the geographical barriers that modern continents impose. The lack of significant barriers facilitated the initial spread of dinosaurs, allowing them to establish populations across vast stretches of Pangaea. As the Mesozoic era progressed into the Jurassic period, around 201 million years ago, Pangaea began to rift apart. This breakup led to the formation of the northern continent Laurasia and the southern continent Gondwana. The division of Pangaea into smaller continents and the development of oceanic barriers could have isolated dinosaur populations, leading to divergent evolutionary paths, a process known as vicariance. This geographical isolation is one of the key factors that drove the diversification of dinosaur species, as populations adapted to their specific environments. Throughout the Jurassic and into the Cretaceous period, the continents continued to drift apart, reaching positions increasingly similar to today's arrangement. This continued movement created new habitats and ecological niches, further encouraging the evolution of specialized dinosaur species adapted to a wide range of environments. For example, the spread of herbivorous dinosaurs into new areas with different plant life would have led to the evolution of various feeding adaptations. Moreover, land bridges and temporary connections between continents, such as those that occasionally linked North America and Asia or Europe and Africa, allowed for additional waves of migration. These connections provided pathways for dinosaurs and other organisms to spread between continents, exchanging genetic material and contributing to the global diversity of dinosaur species. The spread of dinosaurs across the continents is also reflected in the fossil record, which shows similar dinosaur species on now separated continents. For instance, fossils of late Jurassic theropods related to Allosaurus have been found in both North America and Europe, suggesting a common ancestry before the final separation of these landmasses. The differences between dinosaurs in various regions highlight the incredible diversity and adaptability of these ancient creatures to a wide array of environments across the globe. As the continents shifted and drifted apart during the Mesozoic era, dinosaurs found themselves in a variety of climates and habitats, leading to distinct evolutionary paths and adaptations unique to their specific locales. In North America, the late Cretaceous period was home to a diverse array of dinosaur species, including the fearsome Tyrannosaurus rex, the horned Triceratops, and the duck-billed hadrosaurs like Edmontosaurus. These dinosaurs were part of a rich ecosystem that included vast coastal plains teeming with life. The presence of large predators like T-Rex, alongside a variety of herbivorous dinosaurs, suggests a complex food web and dynamic interactions among species. The continent's varied landscape, from lush floodplains to ancient coastal margins, provided a wealth of resources for these dinosaurs to exploit. In contrast, the dinosaurs of South America during the same period included some of the largest sauropods ever to walk the Earth, such as Argentinosaurus and Patagotitan. These gigantic herbivores thrived in the continent's rich, fertile environments, which supported their massive sizes. South America's isolation from other landmasses during much of the Mesozoic era allowed for the evolution of unique dinosaur faunas, including specialized carnivores like the Abelisaurus, which filled the apex predator niche in the absence of tyrannosaurids. Asia, during the late Cretaceous period, was home to a remarkable variety of dinosaurs, including the feathered theropods like Velociraptor, which inhabited the desert environments of what is now Mongolia. The discovery of numerous feathered dinosaur species in China has provided invaluable insights into the evolutionary relationship between dinosaurs and birds. These regions were also home to some of the earliest known horned dinosaurs, or ceratopsians, suggesting that Asia played a critical role in the early evolution of this group. Europe, during the same time, was a series of large islands rather than a single contiguous landmass, leading to the evolution of distinct dinosaur species adapted to island life. This insular environment promoted dwarfism in some dinosaur species, such as the small-sized iguanodon relatives found in Spain, which contrasted with their larger relatives on other continents. The isolation of these island ecosystems allowed for unique evolutionary experiments, resulting in dinosaurs that were distinctly European. Africa, with its ancient landscapes that ranged from Sahara-like deserts to lush river deltas, was home to a diverse array of dinosaur life, including the Spinosaurus, the largest known carnivorous dinosaur. Adapted to a semi-aquatic lifestyle, Spinosaurus is a testament to the diverse adaptations dinosaurs developed to thrive in specific environmental niches. Africa's dinosaur fauna also included massive sauropods and a variety of predatory theropods, showcasing the continent's role as a cradle of dinosaur diversity. There were also so-called polar dinosaurs that lived during various periods of the Mesozoic era, including the Cretaceous period, when parts of what are now Alaska, Australia, and Antarctica were much closer to the poles. Despite being closer to the poles, these regions were not as frigid and ice-covered as they are today. The climate was cooler than the equatorial regions where dinosaurs also thrived, but it was still relatively mild, thanks to the Earth's overall warmer climate during the Mesozoic. However, polar regions experienced extreme seasonal variations, with long, dark winters and summers of continuous daylight. To survive in these challenging conditions, polar dinosaurs developed several unique adaptations. One of the key survival strategies was likely their ability to regulate their body temperatures. While the debate continues on whether all dinosaurs were warm-blooded, endothermic, like mammals or birds, or cold-blooded, ectothermic, like modern reptiles, it's possible that polar dinosaurs had some level of metabolic control over their body temperature. This ability would have been crucial for surviving the cold, dark winters. Another adaptation that may have aided polar dinosaurs is the possibility of seasonal behavioral changes, such as migration. Some species might have migrated to warmer regions during the coldest months, although the evidence for large-scale migration among polar dinosaurs is still a topic of research. Alternatively, they could have had changes in their activity levels or dietary habits to cope with the varying availability of food throughout the year. The diet of polar dinosaurs also suggests adaptability. Herbivorous dinosaurs living in polar regions would have had to rely on plants that could withstand cooler climates and periods of low light. This might have included evergreen conifers and ginkgos, which were prevalent during the Mesozoic era. Carnivorous dinosaurs, on the other hand, would have preyed on the herbivores or scavenged, possibly benefiting from the continuous summer daylight to hunt for extended periods. Fossil evidence, including preserved stomach contents and coprolites, fossilized dung, provides clues about the diets of polar dinosaurs and how they might have changed seasonally to adapt to the available resources. Moreover, the discovery of dinosaur nests and fossils of young dinosaurs in polar regions suggests that some species bred and raised their young in these high latitudes, indicating a year-round adaptation to the polar environment. Among the dinosaurs, several formidable predators stood at the top of the food chain, each employing unique hunting strategies to dominate their respective environments. These top predators were highly adapted for capturing and consuming prey, showcasing a range of evolutionary innovations that made them efficient hunters. One of the most iconic top predators was the Tyrannosaurus rex, which lived in North America during the late Cretaceous period. The T-Rex is renowned for its massive size, powerful jaws, and sharp serrated teeth, which could grow up to 12 inches long. These physical attributes suggest that T-Rex was capable of delivering fatal bites to its prey, causing severe damage and blood loss. Despite debates about whether it was a scavenger or a hunter, evidence points to T-Rex being an opportunistic predator, likely attacking live prey when the opportunity arose and scavenging when it did not. Its strong legs and relatively fast speed for its size would have allowed it to ambush or pursue prey over short distances. In the same period but on a different continent, Spinosaurus aegypticus roamed what is now North Africa. Spinosaurus is unique among known dinosaurs for its semi-aquatic lifestyle, adapted to hunting both on land and in water. Its long, crocodile-like jaws and conical teeth were perfect for catching fish, and recent evidence suggests it spent much of its time in rivers and lakes hunting aquatic prey. This adaptation to a partially aquatic lifestyle is unparalleled among other large theropods, making Spinosaurus one of the most specialized top predators. Another formidable predator was the Allosaurus, which lived during the late Jurassic period in North America. Allosaurus was smaller than T-Rex, but was nonetheless a fearsome hunter. It had a large skull equipped with dozens of sharp teeth and powerful neck muscles, suggesting a hunting strategy that involved biting and tearing flesh from its prey. Allosaurus may have hunted in packs, according to some interpretations of fossil evidence, which would have allowed it to take down large sauropods and other well-defended herbivores. The Cretaceous period also saw the emergence of the Giganotosaurus in South America, one of the largest meat-eating dinosaurs ever discovered. Giganotosaurus was even larger than T. rex and likely preyed on the giant sauropods that inhabited the same region. Its size, powerful legs, and sharp teeth suggest it was a formidable predator capable of taking down some of the largest herbivores of its time. These top predators employed a variety of hunting strategies, from ambush tactics to possibly hunting in packs and exploiting specific environmental niches to target certain prey. Their physical adaptations, including sharp teeth for tearing flesh, powerful limbs for chasing or ambushing prey, and in the case of Spinosaurus, adaptations for an aquatic lifestyle, made them the apex predators of their respective ecosystems. The coexistence of large predators with other dinosaurs is a testament to the complex and balanced ecosystems that characterized the Mesozoic era. Various factors enabled these formidable hunters to share their environments with a diversity of other dinosaur species, including prey, competitors, and even other predators. Understanding how these large carnivores coexisted with other dinosaurs involves examining their diets, territorial behaviors, and ecological niches. Large predators, such as the Tyrannosaurus rex and the Allosaurus, occupied the top of the food chain in their respective ecosystems. Their survival depended on the availability of prey, which included a variety of herbivorous dinosaurs. The prey species varied in size from small, agile ornithopods to massive sauropods. This diversity in prey size and behavior likely helped prevent any single predator species from overhunting a particular prey species, thus maintaining a balance within the ecosystem. The existence of varied habitats within these ancient ecosystems also facilitated coexistence. Different predators adapted to specific environments where they were most efficient at hunting. For example, some large theropods may have preferred open plains where they could use their speed to chase down prey, while others, like the Spinosaurus, adapted to hunting in aquatic or semi-aquatic environments. This specialization allowed large predators to exploit different food sources and reduce direct competition for resources. Territorial behavior played a significant role in how large predators coexisted with each other. Like modern carnivores, large dinosaur predators likely had territories that they defended against rivals. This territoriality would have helped to space out predator populations, reducing competition for food within a given area. Evidence for such behavior is mostly speculative, as it is difficult to prove from the fossil record. But modern analogues in predator behavior provide a plausible basis for this theory. Seasonal migrations of herbivorous dinosaurs could have also supported the coexistence of multiple large predators. Herds of herbivores moving between feeding and breeding grounds would ensure a moving food source, preventing overexploitation of local resources. Predators might have followed these migrations or waited at strategic points along migration routes to ambush the passing herds. The presence of scavenging opportunities would have allowed different carnivorous dinosaurs to feed without always needing to make a kill. Large predators could scavenge from carcasses left by others or from natural deaths within herbivore populations, providing a supplemental food source that reduced the pressure on live prey populations. The staggered appearance of different large predator species across the Mesozoic timeline meant that ecosystems were continually evolving. As some predator species became extinct, others emerged, filling the vacated niches. This dynamic equilibrium allowed for the long-term coexistence of diverse dinosaur communities, including multiple large predators, herbivores, and smaller carnivores, each playing a role in the complex web of life that characterized the age of dinosaurs. The effectiveness of large dinosaur predators in their environments was a result of a series of remarkable adaptations that evolved over millions of years. These adaptations not only made them formidable hunters, but also ensured their survival in the competitive and ever-changing ecosystems of the Mesozoic era. Understanding these adaptations provides insight into the natural history of these incredible creatures and the ecological niches they occupied. One key adaptation was their sophisticated sensory systems. Large predators like the Tyrannosaurus rex had forward-facing eyes, providing them with binocular vision, which is crucial for depth perception and accurately gauging the distance to their prey. This visual acuity would have been particularly advantageous for tracking moving targets. Additionally, Evidence suggests that many of these predators had excellent hearing and a keen sense of smell, enabling them to detect prey from long distances or even to scavenge carcasses. The teeth and jaws of large carnivorous dinosaurs were also highly specialized for their predatory lifestyles. Tyrannosaurs, for example, possessed large banana-shaped teeth with serrated edges, perfect for tearing through flesh and bone. The powerful jaw muscles allowed them to deliver one of the most powerful bites in the animal kingdom, capable of crushing bone and slicing through the toughest armor of herbivorous dinosaurs. The limb adaptations of these predators were critical for their hunting strategies. The long, strong legs of theropods like the Allosaurus enabled them to cover ground quickly, either to ambush prey or engage in sustained pursuits. Some species had specialized claws, like the sickle-shaped claw of the velociraptor, which could have been used to slash at or grip onto prey, inflicting deep wounds. Another significant adaptation was the development of complex social behaviors in some predatory dinosaurs, which may have included pack hunting. While direct evidence for pack behavior is challenging to confirm, the discovery of multiple individuals of species like Allosaurus at the same fossil sites suggests that these dinosaurs may have hunted in groups, allowing them to take down larger prey than they could have managed alone. This social cooperation would have been a considerable advantage in capturing the large, well-defended herbivores of the time. Body size itself was an adaptation that varied among large predators, with each size offering different advantages. Larger predators could take down bigger prey and were less likely to be challenged by other carnivores, while smaller predators benefited from greater agility and the ability to exploit a wider range of prey, including juvenile dinosaurs and smaller species. Some predators exhibited adaptations for specific environmental conditions. For instance, Spinosaurus is believed to have been semi-aquatic, with adaptations such as a long, crocodile-like jaw and dense bones that allowed it to hunt both in water and on land. This versatility would have given it access to a unique prey niche compared to its entirely terrestrial counterparts. The Mesozoic era witnessed an incredible diversity of plant-eating dinosaurs that filled various ecological niches across the globe. These herbivorous dinosaurs evolved a multitude of adaptations that allowed them to feed on the wide array of vegetation present in their environments, from lush ferns and cycads to towering conifers, and later, flowering plants. The variety of plant-eating dinosaurs included massive sauropods, armored ankylosaurs, beaked hadrosaurs, and horned ceratopsians, among others. Sauropods, such as Brachiosaurus, Apatosaurus, and Diplodocus, were among the most iconic plant-eaters and are renowned for their enormous size. These gentle giants possessed long necks that allowed them to reach high into trees to feed on foliage that was out of reach for other herbivores. Their pillar-like legs supported their massive bodies, and they had relatively small heads with simple peg-like teeth suitable for stripping leaves off branches. Sauropods were believed to have a slow digestive system, with large fermenting guts that could break down tough plant material. Ankylosaurs, including Ankylosaurus and Euoplocephalus, were armored dinosaurs known for their heavy body armor and club-like tails, which they used for defense against predators. Their bodies were covered in bony plates, and some species had spikes for added protection. These dinosaurs were low browsers, feeding on ground-level vegetation. They had small teeth and wide, grinding surfaces that were likely used to process tough, fibrous plants. Hadrosaurs, or duck-billed dinosaurs, such as Edmontosaurus and Parasaurolophus, were another group of herbivores that thrived during the late Cretaceous. They had specialized teeth arranged in a way that formed a continuous grinding surface, allowing them to chew their food thoroughly, a relatively advanced feature among dinosaurs. Their broad, duck-like beaks were used to strip leaves and twigs from trees and bushes. Ceratopsians like Triceratops and Styracosaurus were characterized by their large frills and facial horns, which were likely used for defense and possibly for display during mating rituals. These dinosaurs had beaked mouths that were efficient at clipping vegetation, and their complex teeth were capable of grinding tough plant material. They were primarily low browsers, feeding on ferns, cycads, and the low-growing leaves of conifers. Stegosaurs, such as Stegosaurus, with their distinctive rows of bony plates and spiked tails, were another group of herbivorous dinosaurs. These dinosaurs had small heads and simple peg-like teeth, suggesting a diet of soft vegetation. The function of their plates has been debated, with theories suggesting they were used for display, thermoregulation, or defense. These diverse groups of plant-eating dinosaurs not only illustrate the wide array of feeding adaptations that evolved among dinosaurs, but also highlight the complexity of Mesozoic ecosystems. Their existence provided the foundation for a dynamic food web, with each group occupying specific niches that minimized competition for resources. Herbivorous dinosaurs employed a variety of strategies to defend themselves against the predators of their time, showcasing the evolutionary arms race between predator and prey during the Mesozoic era. These defense mechanisms ranged from physical adaptations like armor and horns to behavioral strategies such as herd living and possibly even camouflage. Each adaptation provided these plant eaters with a means to survive in a world filled with formidable carnivorous dinosaurs. One of the most visually striking defensive adaptations was the development of armor. Ankylosaurs, such as Ankylosaurus and Euoplocephalus, were essentially living tanks. Their bodies were covered in thick, bony plates known as osteoderms, and many species had spikes or knobs for added protection. The tail club of Ankylosaurs was a formidable weapon, capable of delivering powerful blows to deter or injure predators. This heavy armor made Ankylosaurs one of the least palatable choices for predators. Ceratopsians, like Triceratops and Styracosaurus, used their large horns and frills as defensive tools. The horns could have been used to charge at predators or to fend off attacks, while the frills might have provided protection for the neck and acted as a display to intimidate potential threats. The sheer size and strength of ceratopsians, combined with their defensive headgear, made them challenging prey for even the largest predators. Stegosaurs, such as Stegosaurus, had rows of large, bony plates along their backs, which might have been used for display or thermoregulation, and spikes at the end of their tails known as thagomizers. These spikes could be swung at predators, inflicting serious injuries. The placement of the spikes at the tail's end suggests that stegosaurs could have used their tails as flexible weapons, keeping predators at bay while minimizing risk to themselves. Hadrosaurs, or duck-billed dinosaurs, and sauropods like Brachiosaurus and Diplodocus may have relied more on behavioral strategies for defense. These dinosaurs often lived in herds, which could have provided safety in numbers. Being in a group means that there are more eyes to spot danger, and large congregations of individuals can confuse or deter predators. Some hadrosaurs also possessed crests that might have been used to produce loud sounds, potentially to warn others of danger or scare off smaller predators. Camouflage is another possible defense strategy, although direct evidence for this is harder to ascertain from the fossil record. However, the discovery of preserved skin patterns and colors in some dinosaur species suggests that camouflage could have been used to blend into their environments, hiding from predators in plain sight. The evolution of flowering plants, or angiosperms, during the Cretaceous period had a profound impact on the ecosystems of the time and consequently on the herbivorous dinosaurs that inhabited them. Before the widespread appearance of flowering plants, the landscape was dominated by gymnosperms, such as conifers, cycads, and ginkgos, which had been the primary food sources for many herbivorous dinosaurs. The advent of angiosperms introduced a significant change in the variety and availability of plant life, offering new dietary options and potentially influencing the evolution of the dinosaurs that fed on these plants. Flowering plants are characterized by their rapid life cycles and the ability to inhabit a wide range of environments. This versatility allowed them to spread quickly across many regions, diversifying the plant life available to herbivorous dinosaurs. As angiosperms became more prevalent, they likely provided a more nutritious and energy-rich food source than the tough, fibrous gymnosperms that had previously dominated the landscape. This shift could have supported larger populations of herbivores and may have driven the evolution of new feeding strategies and adaptations. One of the direct effects of the evolution of flowering plants on herbivorous dinosaurs was the potential development of more complex digestive systems. To process the diverse range of plant materials efficiently, including the hard seeds and fleshy fruits produced by angiosperms, some dinosaurs might have evolved more sophisticated methods of digestion. This could include the development of specialized teeth for grinding seeds and fruits, as well as changes in gut morphology to better ferment and extract nutrients from a varied diet. Additionally, the spread of flowering plants might have influenced the social behavior and migratory patterns of herbivorous dinosaurs. As these plants colonized different environments, herbivores may have followed, leading to the exploration of new territories and possibly even the establishment of migratory routes to take advantage of seasonal blooms. This dynamic could have fostered greater mobility among herbivorous dinosaur populations, affecting their distribution and interaction with the surrounding ecosystems. The diversification of angiosperms also likely led to an increase in the complexity of Mesozoic ecosystems. With more plant species occupying various ecological niches, herbivorous dinosaurs would have had to adapt to exploit these new resources. This might have driven the evolution of dietary specialization in some dinosaur groups, leading to a more intricate web of predator-prey relationships and interspecies competition. Furthermore, the evolution of flowering plants had implications beyond the immediate dietary benefits for herbivorous dinosaurs. The rise of angiosperms is associated with the development of co-evolutionary relationships with pollinators, which could have added another layer of complexity to the ecosystems of the time. While dinosaurs are not typically thought of as pollinators, the changes in plant life would have indirectly influenced dinosaur populations by affecting the entire food web, from insects and other small animals up to the largest herbivores and their predators. Dinosaurs, as the dominant terrestrial vertebrates for over 160 million years, had a profound impact on the ecosystems they inhabited. Their presence influenced the structure of communities, the distribution of plant life, and the evolutionary trajectories of other organisms sharing their environments. Understanding the impact of dinosaurs on their ecosystems involves examining their roles as herbivores, predators, and engineers of their habitats, as well as considering their interactions with the plant and animal life of the Mesozoic era. As herbivores, dinosaurs played a critical role in shaping the vegetation of their ecosystems. The feeding habits of large sauropods, for example, would have affected the types of plants that thrived in certain areas. By consuming large quantities of vegetation, these dinosaurs acted as natural pruners, potentially controlling plant growth and encouraging a diversity of plant species. Their ability to reach high into the trees and consume parts of plants that other herbivores could not also meant they could influence the structure and composition of forests. The digestion and subsequent dispersal of seeds through their feces could have contributed to the spreading of plant species across various landscapes. Predatory dinosaurs, on the other hand, played the role of population control, keeping herbivorous dinosaur numbers in check. This predator-prey dynamic was essential for maintaining balanced ecosystems, preventing any one species from becoming too dominant and depleting resources. The hunting strategies and behaviors of carnivorous dinosaurs would have also influenced the evolution of defensive mechanisms in herbivores, such as the development of armor, horns, and social behaviors aimed at protection from predators. Dinosaurs could also be considered ecosystem engineers, organisms that create, modify, or maintain habitats in ways that benefit other species. The movement of large dinosaurs through their environments could have affected the physical landscape, creating paths that might be used by other animals and altering the distribution of water and nutrients in the soil. The nesting behaviors of some dinosaurs, which involved digging and the construction of nests, could have influenced soil composition and vegetation patterns. The sheer biomass of dinosaurs would have had significant implications for the ecosystems they were part of. The decay of deceased dinosaurs would have been a substantial source of nutrients for decomposers, contributing to nutrient cycling and soil fertility. This, in turn, would have supported plant growth and the overall productivity of the ecosystem. The extinction of dinosaurs at the end of the Cretaceous period illustrates their critical role in ecosystems. Their disappearance led to significant changes in the ecological landscape, opening niches for other groups of animals, particularly mammals, to fill. This shift allowed for the diversification and evolution of mammalian species, eventually leading to the dominance of mammals in post-Mesozoic ecosystems. Dinosaurs' interactions with other species, including early mammals during the Mesozoic era, played a significant role in shaping the biodiversity of that time. These interactions were complex and varied, ranging from predation and competition to potentially symbiotic relationships. Understanding these dynamics provides insight into the intricate web of life that existed millions of years ago and the ecological roles dinosaurs and other species played within it. Predation was one of the most direct forms of interaction between dinosaurs and other species. Carnivorous dinosaurs, as apex predators, preyed on a wide variety of organisms, including smaller dinosaurs, reptiles, amphibians, and early mammals. The presence of these predators influenced the behavior and evolutionary adaptations of prey species, leading to the development of defensive mechanisms such as speed, camouflage, armor, and social behaviors aimed at reducing the risk of predation. For instance, the evolution of nocturnal habits among some early mammals has been suggested as a strategy to avoid predation by dinosaurs, exploiting niches that were less dangerous during the night. Competition for resources was another form of interaction, not only among different species of dinosaurs, but also between dinosaurs and other vertebrates, including early mammals. While dinosaurs were the dominant terrestrial vertebrates, early mammals occupied various ecological niches that sometimes overlapped with those of smaller dinosaurs. This competition could have driven the diversification and specialization of species as they evolved to exploit different resources more efficiently, minimizing direct competition. Early mammals, for instance, might have adapted to feeding on resources that were less contested by dinosaurs, such as insects or plants not typically consumed by herbivorous dinosaurs. Though less documented, there could have been symbiotic interactions between dinosaurs and other species, including early mammals. For example, some dinosaurs might have acted as ecosystem engineers, creating habitats that benefited other organisms. The disturbance of vegetation by large herbivorous dinosaurs could have fostered new growth that provided food for smaller herbivores, including early mammals. Similarly, the dung of large dinosaurs would have been a nutrient-rich resource that supported a variety of decomposers and possibly provided food for dung-feeding organisms. The relationship between dinosaurs and plant life was also a form of interaction that had broader implications for the ecosystem. Dinosaurs acted as agents of seed dispersal and pollination for certain plants, facilitating the spread and diversity of flora. This interaction was mutually beneficial, as plants provided a food source for herbivorous dinosaurs, while the dinosaurs helped in the reproduction and spread of plant species. As the Mesozoic era progressed, the dynamics of competition evolved. By the Jurassic period, dinosaurs had become the dominant terrestrial vertebrates, but this dominance did not go uncontested. The skies were the domain of the pterosaurs, flying reptiles that soared above the dinosaurs' heads, hunting for insects and smaller prey. Though not in direct competition for ground-based resources, the existence of pterosaurs exemplifies the diversity of reptilian life that coexisted with dinosaurs, each group finding its unique way to thrive. The seas told a similar story of diversity and competition. Marine reptiles like the ichthyosaurs, plesiosaurs, and mosasaurs ruled the oceans. These aquatic giants were as formidable in the water as the largest dinosaurs were on land. They hunted fish, squid, and other marine life, establishing a parallel predator-prey dynamic in the Earth's vast seas. While they did not compete with terrestrial dinosaurs for food, their evolutionary success highlights the competitive pressures that shaped life in all environments of the Mesozoic world. In the later stages of the Mesozoic, the Cretaceous period introduced new players to the scene. The rise of crocodiliforms, particularly those resembling modern crocodiles, added another layer of competition. These reptiles, with their powerful jaws and aquatic prowess, could have competed with dinosaurs for prey along riverbanks and shorelines. The presence of these and other reptilian groups underscores the competitive pressures that were constant in the evolutionary saga of the Mesozoic era. Despite the competition, or perhaps because of it, Dinosaurs and their reptilian contemporaries evolved a wide array of adaptations that allowed them to exploit different ecological niches. From the air to the sea to the varied landscapes of the ancient Earth, the Mesozoic era was a time of remarkable biodiversity. The competition among dinosaurs and other reptiles drove evolutionary innovations, leading to the incredible variety of life forms that populated the planet during this golden age of reptiles. Throughout their existence, dinosaurs encountered several major extinction events before facing their ultimate demise. These events profoundly shaped the course of dinosaur evolution and biodiversity on Earth. One of the most significant extinction events occurred at the end of the Permian period, around 252 million years ago, known as the Permian-Triassic extinction event. This catastrophic event resulted in the loss of approximately 90% of marine species and 70% of terrestrial vertebrate species, including many early reptiles and amphibians. While dinosaurs did not yet exist during this extinction event, it cleared the way for their eventual rise by eliminating competitors and creating ecological opportunities. The next significant extinction event occurred at the end of the Triassic period, approximately 201 million years ago, known as the Triassic-Jurassic extinction event. While not as severe as the Permian-Triassic event, this extinction still had a notable impact on biodiversity. It resulted in the disappearance of numerous reptilian groups, including some large amphibians and early mammal-like reptiles, paving the way for dinosaurs to become the dominant terrestrial vertebrates during the Jurassic period. Following the Triassic-Jurassic extinction, dinosaurs experienced a period of dominance and diversification during the Jurassic and early Cretaceous periods. However, another major extinction event occurred approximately 66 million years ago, marking the end of the Cretaceous period, known as the Cretaceous-Paleogene (KPG) extinction event. This event is infamous for leading to the extinction of non-avian dinosaurs, as well as many other organisms, including marine reptiles, flying reptiles, pterosaurs, and numerous plant and invertebrate species. The exact causes of the KPG extinction event are still debated, but it is widely believed to have been triggered by a combination of factors, including a massive asteroid impact, volcanic activity, and climate change. The KPG extinction event had a profound and lasting impact on Earth's ecosystems, reshaping terrestrial and marine environments and paving the way for the rise of mammals and birds as the dominant vertebrate groups. While dinosaurs faced challenges and extinction events throughout their existence, they were remarkably successful for over 160 million years before ultimately succumbing to the catastrophic events of the KPG extinction. This event marked the end of the Mesozoic era and the dawn of the Cenozoic era, during which mammals rose to prominence and diversified to fill the ecological niches left vacant by the demise of the dinosaurs. These extinction events played a crucial role in shaping the course of dinosaur evolution over millions of years. The Permian-Triassic extinction event, for instance, wiped out many of the dominant reptilian groups that existed before dinosaurs, creating ecological opportunities for their eventual rise. Dinosaurs emerged during the aftermath of this extinction, taking advantage of the vacant niches left by the extinction of competing species. This allowed them to diversify and evolve into a wide array of forms, ranging from small, agile predators to massive, long-necked herbivores. The Triassic-Jurassic extinction event further influenced dinosaur evolution by eliminating many of the remaining competitors and paving the way for their dominance during the Jurassic period. With fewer competing reptilian groups, dinosaurs were able to expand into new ecological roles and environments, leading to the emergence of iconic species like the sauropods and theropods. However, it was the catastrophic Cretaceous-Paleogene (KPG) extinction event that ultimately brought an end to the reign of the dinosaurs. This event, likely triggered by a combination of factors including an asteroid impact, volcanic activity, and climate change, led to widespread devastation and the extinction of approximately 75% of all species on Earth, including the non-avian dinosaurs. The sudden loss of these dominant terrestrial vertebrates created opportunities for other groups, such as mammals and birds, to thrive and diversify in the aftermath of the extinction. The End Cretaceous extinction event is one of the most studied extinction events in Earth's history. Scientists have gathered various lines of evidence to understand its cause. One major piece of evidence is the discovery of a layer of sediment enriched in the element iridium, found in numerous locations around the world and dating back to the time of the extinction event. Iridium is rare in Earth's crust, but is abundant in extraterrestrial objects like asteroids and comets. This discovery led scientists to propose that a massive asteroid impact occurred around the time of the extinction. Further evidence supporting the asteroid impact hypothesis includes the presence of shocked quartz and microscopic diamonds in sediment layers dating to the KPG boundary. These minerals form under extreme pressure and are often associated with impact events. Additionally, researchers have identified impact craters from around the same time period, such as the Chicxulub crater off the coast of Mexico's Yucatan Peninsula. The size and location of the Chicxulub crater suggest that it could be the result of the impact that triggered the End Cretaceous extinction event. In addition to the asteroid impact hypothesis, scientists also consider other factors that may have contributed to the extinction event. Volcanic activity, particularly the massive eruptions of the Deccan Traps in present-day India, likely released large amounts of ash, gases, and aerosols into the atmosphere, leading to environmental disruptions and climate changes. These volcanic eruptions may have acted in conjunction with the asteroid impact to exacerbate the effects of the extinction event. So what really happened on the last day of the dinosaurs? On this fateful day, the Earth would have looked much different from the world we know today. The climate was warmer, and the continents were arranged differently, with vast inland seas and lush tropical forests covering much of the land. Dinosaurs roamed diverse ecosystems, ranging from dense forests to open plains, adapting to a variety of niches and ecological roles. The precise sequence of events on the final day of the dinosaurs remains uncertain, but the impact of an asteroid or comet likely set off a chain reaction of catastrophic events. As the asteroid collided with the Earth's surface, it released an immense amount of energy, causing widespread devastation. The impact would have generated intense heat, triggering wildfires that engulfed large areas of vegetation. The force of the impact also generated seismic waves and massive tsunamis, which swept across coastlines and inundated low-lying areas. The release of vaporized rock and debris into the atmosphere created a global dust cloud, blocking out sunlight and causing a dramatic drop in temperatures, a phenomenon known as impact winter. This prolonged period of darkness and cold would have disrupted photosynthesis, leading to the collapse of ecosystems and the extinction of many plant and animal species. In the aftermath of the End Cretaceous extinction event, the Earth underwent significant changes that reshaped its ecosystems and set the stage for the rise of new life forms. The consequences of this catastrophic event were far-reaching and profound, leaving a lasting impact on the planet's biodiversity and evolutionary trajectory. One of the immediate consequences of the extinction event was the widespread loss of species diversity. Not only did the non-avian dinosaurs disappear from the fossil record, but numerous other plant and animal species also went extinct. This loss of biodiversity disrupted ecological relationships and led to the collapse of food webs, with ripple effects felt throughout ecosystems worldwide. The disappearance of dominant groups of organisms created ecological opportunities for surviving species to fill vacant niches and adapt to new environmental conditions. Mammals, which had previously occupied relatively minor roles in ecosystems, underwent a remarkable diversification during the aftermath of the extinction event. With less competition from dinosaurs and other large reptiles, mammals were able to exploit new ecological roles and evolve into a diverse array of forms. In addition to the rise of mammals, other groups of organisms, such as birds and flowering plants, also experienced significant evolutionary radiations in the wake of the extinction event. Birds, which are the modern descendants of small theropod dinosaurs, diversified and expanded into various habitats, ultimately becoming one of the most successful groups of vertebrates on Earth. Meanwhile, flowering plants underwent a rapid diversification, transforming terrestrial landscapes and giving rise to the lush forests and diverse ecosystems that characterize much of the modern world. The end Cretaceous extinction event also had profound implications for the Earth's geology and climate. The impact of the asteroid or comet, along with subsequent volcanic activity and environmental changes, altered atmospheric composition and global climate patterns. In the aftermath of the extinction event, the Earth experienced a period of cooling and instability known as the Paleocene-Eocene thermal maximum, which had significant effects on marine and terrestrial ecosystems. The aftermath of the end Cretaceous extinction event marked a pivotal moment in Earth's history, shaping the course of evolution and leading to the emergence of modern ecosystems and the rich diversity of life that exists today. Fast-forwarding hundreds of millions of years, we end up here, today's date. With the help of new technology and tools, paleontologists, scientists who study ancient life, employ various methods to find and excavate dinosaur fossils. One common approach is to search for fossils in sedimentary rock layers that formed during the Mesozoic era, the time when dinosaurs roamed the Earth. These rocks often contain fossilized remains of dinosaurs and other ancient organisms. To locate potential fossil sites, paleontologists may use geological maps, satellite imagery, and knowledge of rock formations to identify areas where sedimentary rocks of the right age are exposed at the Earth's surface. Once a promising site is identified, the painstaking process of excavation begins. Excavating dinosaur fossils requires careful planning and attention to detail. Paleontologists typically use tools such as picks, brushes, and shovels to carefully remove layers of rock surrounding the fossilized remains. Sometimes, heavy machinery like backhoes or jackhammers may be used to help break through tough rock layers, but manual excavation is often necessary to avoid damaging delicate fossils. As fossils are uncovered, they are carefully documented and labeled to keep track of their exact position within the rock layer. This information is crucial for understanding the fossil's context and interpreting its significance. Once all the fossils at a site have been excavated, they are transported to a laboratory for further study and preparation. In the lab, paleontologists clean and prepare the fossils by removing any remaining rock matrix and stabilizing fragile bones. This process can take months or even years, depending on the size and condition of the fossils. After preparation, the fossils are studied in detail to learn more about the ancient organisms they represent. This may involve comparing them to known species, analyzing their anatomy and morphology, and conducting various scientific tests to gather additional information. Dating dinosaur fossils is a crucial aspect of paleontology, helping scientists understand when these ancient creatures lived and how they fit into Earth's history. Several techniques are used to determine the age of dinosaur fossils, each relying on different principles of geology and chemistry. One common method is relative dating, which involves comparing the ages of fossils found in different rock layers. By studying the sequence of sedimentary rock layers, scientists can determine the relative ages of fossils based on their position in the rock record. This technique provides a general idea of when dinosaurs lived relative to other organisms and geological events. Another widely used dating method is radiometric dating, which relies on the decay of radioactive isotopes in rocks and minerals. One commonly used radioactive isotope for dating rocks is uranium-238, which decays into lead-206 at a known rate. By measuring the ratio of uranium to lead in a sample, scientists can calculate its age based on the known decay rate. This technique, known as uranium-lead dating, is often used to date the volcanic rocks associated with dinosaur fossils. In addition to uranium-lead dating, other radiometric dating methods such as potassium-argon dating and argon-argon dating can also be used to date rocks and fossils. These methods rely on the decay of potassium-40 into argon-40 and are commonly applied to volcanic ash layers that are interbedded with fossil-bearing sedimentary rocks. Paleontologists may also use stratigraphic correlation to date dinosaur fossils. This involves comparing the ages of fossils found in different locations and correlating them based on similarities in the rock layers. By studying the distribution of fossils across different regions, scientists can create a timeline of dinosaur evolution and migration. Our understanding of dinosaurs has evolved significantly over time, driven by ongoing scientific research and discoveries. Initially, dinosaurs were thought to be slow-moving, cold-blooded reptiles resembling modern-day lizards. However, as paleontologists unearthed more fossils and analyzed new evidence, our perception of dinosaurs underwent dramatic changes. One of the most significant shifts in our understanding of dinosaurs came with the recognition that they were more closely related to birds than reptiles. This idea gained traction in the late 20th century and is now widely accepted within the scientific community. Evidence supporting this connection includes similarities in skeletal structure, such as hollow bones, wishbones, and feathers found in some dinosaur fossils. Our understanding of dinosaur behavior has evolved over time. Early depictions portrayed dinosaurs as sluggish, lumbering creatures, but evidence suggests that many dinosaurs were agile and active animals. Fossilized trackways indicate that some dinosaurs moved in herds, while others may have been solitary hunters. Additionally, studies of dinosaur nesting sites and parental care behaviors have provided insights into their reproductive strategies and social interactions. Advancements in technology have also revolutionized the study of dinosaurs. Techniques such as computed tomography, CT scanning, and three-dimensional modeling allow scientists to examine fossils in unprecedented detail without damaging them. These tools have revealed internal structures, such as brain cavities and air sacs, providing further clues about dinosaur physiology and behavior. Our understanding of dinosaur diversity and evolution has expanded with the discovery of new species and the refinement of classification methods. Paleontologists now recognize a wide range of dinosaur groups, each adapted to different ecological niches and habitats. By studying these diverse forms, scientists can piece together the evolutionary history of dinosaurs and their role in shaping ancient ecosystems. Is it possible to bring dinosaurs back to life? While the idea of bringing dinosaurs back to life by extracting and replicating their DNA might sound like something out of a science fiction movie, the reality is far more complex. Despite advancements in genetic technology, scientists have not been able to recover intact dinosaur DNA from fossils. This is largely due to the fact that DNA has a limited lifespan and degrades over time, making it extremely unlikely to survive for millions of years. The oldest DNA ever recovered comes from a horse that lived around 700,000 years ago, which is still far more recent than the age of dinosaurs. Additionally, even if intact dinosaur DNA were miraculously found, the process of reconstructing an entire genome from fragmented DNA sequences would be exceedingly challenging. As we conclude our journey through the prehistoric world of dinosaurs, we are left with a profound understanding of their rise to dominance and their eventual demise. From their humble beginnings in the Triassic period to their magnificent reign during the Jurassic and Cretaceous periods, dinosaurs captivated the Earth with their incredible diversity and adaptability. But as we've learned, even the mightiest rulers of the ancient world were not immune to the forces of change. The fall of the dinosaurs, marked by catastrophic events like asteroid impacts and volcanic eruptions, serves as a stark reminder of the fragility of life on our planet. It prompts us to reflect on our own place in the natural world and the potential risks that lie ahead. Today, as we confront challenges such as climate change, habitat destruction, and the loss of biodiversity, we are reminded of the importance of understanding and respecting the delicate balance of our planet's ecosystems. Just as the dinosaurs once shaped the course of life on Earth, so too do we hold the power to influence its future. By harnessing the lessons of the past, and leveraging the advancements of modern science and technology, we have the opportunity to mitigate these risks and create a more sustainable future for generations to come. But it requires a collective effort driven by scientific inquiry, environmental stewardship, and a shared commitment to preserving the wonders of our natural world.